Hello, in this video I'll be showing you how to derive the relationship between velocity and area for a converging diverging nozzle, and that relationship of velocity and area depending on the Mach number. So ultimately we want to arrive at this equation here, and to do this we're going to use the conservation of mass, momentum, and some isentropic flow relations. Okay, so let's get started. So the first thing we're going to use is conservation of mass, which basically says at any given point along a system. So let's have I'm just going to elaborate on this quick. So we have our nozzle here. Basically saying conservation of mass, basically saying that the mass flow rate along this entire nozzle, along this entire process, is constant. So we can use m dot, which is mass flow rate, equals rho VA, and that equals constant. So the density of the material times the velocity of the material times the cross-sectional area remains constant the entire way. For the rest of this video, I'm going to be using R instead of rho, just because I'll be introducing a lot of pressures, which I'll be using the symbol P, and I don't want to get rho and P confused because they can look the same. So for rho, for density, I'm just going to be using R the rest of the way. So this equals constant. So if you see R in the rest of this video, that means density. So now I want to differentiate this equation here. So to differentiate across all three of these values, we have VA dr plus RA dV plus RV dA. Okay, it's using the product rule, and then the derivative of a constant, it just equals 0. So we're left with this equation here. But then I want to change the form of this equation. So I'm going to divide everything by RVA, both sides by RVA, which leaves me with the form dr over R plus dV over V plus dA over A equals 0. So let's call that our kind of first equation here, our first result that we'll need to look for later. So now we want to use the conservation of momentum to eventually derive this equation. Rho v dv, or rv dv, equals negative dp. Okay, so you eventually want to derive this equation here. And to do that, we'll use conservation of momentum. Alright, now using conservation of momentum, and to show this, we have a square here. This is just a small kind of, it's hard to describe, but it's just like an infinitesimally small point, okay? It's just showing that velocity coming in and pressure coming in, then coming out, it's velocity plus whatever momentum it gains or pressure it loses, or pressure it gains and velocity it loses, over the distance of this section here. And this section has an area and a density, and we're still using density. Our equation for that is R. So have to draw this out. So this is just the velocity coming in plus whatever the change in velocity is over that span times the span. Okay. So then we're going to use Newton's second law, which, as we know, is force equals mass times acceleration. We can also write this as mass delta V over delta T. So the delta just equals change, so change in velocity over change in time. That equals acceleration. The derivative of velocity with respect to time is acceleration, so we can write it as that. But then we also know force equals PA. So pressure times area. So then we're going to write, so we're going to use those, substitute in force for the pressure in each side. And we're going to write it in this form just because this is the result. This allows a cleaner result. So this is basically just saying, so if you distribute the negative, so PA1 minus PA2 is the net force, and that equals mass times acceleration. Okay, and we're also going to write delta V here as V2 minus V1. So that's the change in velocity. Is the difference, the change in velocity is the difference between side 2 and side 1. So we also know that the pressure at 2 is this. So this equals P2, and this we can also say equals V2. And then P just equals P1, and V equals V1. So you can see that there. Okay, so we're going to substitute that in for our P2, which leaves us negative. We're going to substitute our P1 and P2 into this equation. So you're left with P plus delta P divided by delta X times delta X times area. And also our areas are the same. So A1 equals A2. So we're just going to write that as A minus PA. So that's the pressure at 1 times the pressure times the area at 1. And that equals mass times, then V2 we have V plus delta V over delta X times delta X minus V1, which just equals V. And that's all divided by our delta T. Okay, so this really should be in parentheses. So this is above. Then this simplifies. So this A times the P is PA, so PA minus PA, that disappears. So then we're just left with negative delta P over delta X times delta X and times A. That's set equal to then the V minus the V. Those cancel out. You're just left with M delta V over delta X. And then we're going to separate this delta X over delta T. Okay? So then we're going to use another relationship here. We know that mass equals density times delta X times area. And if you want to check the units, density is kilograms per meter cubed. Delta X is just meters, or a unit of length. There's no units, we're not using units, but just a unit of length. And then obviously the unit of length squared. All those cancel out and you're just left with kilograms, or a unit of mass basically. So it's always good to check your units to make sure you are on the right track. So we're going to substitute M with this R delta XA. So then we're writing P equals R delta X A times delta V over delta X, delta X over delta T. Then the A's, both sides cancel out, and then you're left with negative delta P over delta X equals R. And then the delta X's cancel out. And then you're just left with V So back here, so delta X over delta T equals V. So you take this delta X, that turns into another V, and then we're also left with a delta V term, because these delta X's cancel, but you're still left with this delta X is still there. So you're left with another delta X on the bottom there. So then this can be written in differential form. So negative dP over dx equals RV delta V over delta X. Okay, so delta P, so this is change dP. Sometimes I might say delta when I mean d. So this is just a differential, a change. That's how you can think of it as. And then our delta x's cancel, and you're just left with negative delta pressure equals RV delta V. So that's an important result. And what does this say here? What is this telling you? This is telling you as pressure decreases, the velocity increases. And that makes a lot of sense. You would think that if, so let's say we have a high pressure system here, high pressure, over here we have low pressure, right? Air, let's think of it air, anything, any like a liquid, it wants to go from high pressure to low pressure, right? So as it's going from high to low, so it's the density or pressure is getting lower, that velocity is going to increase. So that's where we get this relationship here. Alright, now we are going to derive these isentropic flow relations, which then we will use plugging back into the momentum equation to ultimately find the relationship between velocity and area as a function of the Mach number. So we want to derive these two relationships here. So quickly, defining isentropic, that means a process is adiabatic and reversible. Adiabatic means that the process in which heat does not enter or leave the system. So we are assuming this is an isentropic process. So then we're going to find an isentropic, I forget what's the exact word, but the Greek letter gamma equals Cp divided by Cv. And sometimes if I get sloppy, I'm going to write this as like Cp, but just think it's C subscript P, which is so Cp is specific heat for constant pressure, and Cv is the specific heat for constant volume. So this is an important relationship here. And then we also can use the relationship that Cp minus Cv equals R, which this is the gas constant from the equation of state, which that is PV equals RT, and we can also write this as pressure equals R times rho, or density, times T. Okay, and this R, so it gets confusing. Sometimes it'll be an R, which could equal 8,314.5 units are like joules. This may be kilojoules per kilomole Kelvin. But this R that we're going to use here, this isn't the universal gas constant. This is the specific gas constant for a certain gas. Okay, so for air you would take 813.5 and divide it by that, the molar mass, and then you would get the R value for air, which I don't know that off the top of my head, but that's what it is. So this is the R we're using. It's this R divided by M equals the R we're using here. Okay. All right. So we're gonna use this relationship here, and then we're gonna divide by Cp. So divide both sides by Cp. Oops, sorry, you can't see that here. And you're just left with 1 minus 1 divided by gamma equals R divided by Cp. Because we know Cv divided by Cp, well, we know Cp divided by Cv is gamma, so that flipped is 1 minus gamma. And then combining these two terms here, we can do gamma over gamma. Sorry, minus 1 divided by gamma equals R divided by Cp, which just leaves us with gamma minus 1 divided by gamma equals R divided by Cp, which then we're going to rewrite as Cp divided by R equals gamma over gamma minus 1. Alright, so now we got this result here. Continuing. For entropy, the equation for entropy, which I don't have time to explain, but that equals ds equals Cp dt over T minus R d dP over P. So this is pressure. For an isentropic relationship, ds equals 0. So this can be written as Cp dt divided by T equals R dP divided by P. Then from our equation of state, T equals P divided by R times the density, which then we're going to plug that into here. So Cp dt divided by P divided by RR equals R dP over P. A lot of things cancel. These pressures cancel. This would be flipped up to here, so these cancel too. This, and then we divide it. So then you're just left with Cp times dt equals delta pressure divided by R. Okay? So this is saying that as pressure increases, your temperature is also going to increase. Okay? Which makes sense. Now, we're going to go all the way up here and then differentiate these two terms. Well, not yet. Okay, so we're going to go back to our relationship here and replace. So we know T. So we know previously T equals P divided by RR. So then we're going to do Cp over R. But then we're going to replace here with this P over R. So we're inserting the T from this equation. We're bringing out the R because that's not going to change, right? This is a universal constant. This is the constant. This isn't changing, but the pressure and the density, those are changing. So we can take that out, but because if we're replacing the T, which is changing, we also have to keep these inside the differential. dP over R. Alright, now we're going to differentiate both sides. P over R. So the derivative of P over R with respect to P is dP over R, and then the derivative of this with respect to R is P dr divided by R squared, and then we just have dP over R. Moving on. So now we're going to just kind of combine some terms here. P divided by R, dP over R, minus, then we're going to bring over this dP minus R, equals Cp over R d dr, or no, P, my bad, P dr divided by R squared. So now that we have this, R cancels, and R cancels. And we can write this as, bring out the like terms, so dP, and then we're going to divide P by both sides. So dP over P, and then you're left with the Cp over R minus 1 equals Cp over R dr divided by R. You're left with this result. Then we're going to substitute in our relationship of Cp over R equals gamma divided by gamma minus 1. Substitute that in there. Alright, so now we're going to do a little math here, combine these. So we have, let's see here, gamma over gamma minus 1 minus gamma minus 1 divided by gamma minus 1. And then this comes out, if you do the math here, these y's cancel out, this becomes a plus. So you're left with 1 over gamma minus 1, dP over P equals gamma over gamma minus 1 dr divided by R. Then divide this by both sides, you're left with dP over P equals And then if you divide this, so divide gamma over gamma minus 1, divided by 1 over gamma minus 1. These two cancel out and you're just left with a gamma divided by r. That's a p. So then you are left with this, which is the result we were looking for. Alright, so now we want to take this relationship and convert it into this. So what you're going to do is we're going to take delta p equals, then we're going to multiply the p to both sides, gamma dr divided by r. And then we're going to use, back to our equations of state, p equals r rt. And then we're going to divide the row, so divided by density, so pressure divided by density equals r times t. Which then we're going to plug that, so we'll take this p over r. Okay, plug that in. With delta pressure equals gamma RT dr. Okay, and then we know, well, I don't know if you know, but the equation for speed of sound, A, equals the square root of gamma RT. So, therefore, A squared equals gamma RT. So, delta pressure equals A squared dr. So now that we got this relationship here, we're going to bring back the relationship we found using conservation of momentum between velocity and pressure, which is RV dV equals negative dP. Okay, so then we're going to plug delta pressure into here. So we have negative A squared dr equals RV dV. Divide by your negative A squared on both sides and your R. So we're going to be left with A squared dr RV dV. So after manipulating some terms, we got V over A squared dV equals dr divided by r, and have the negative on the dr. So all we did was divided by r over here and divided this by A squared. Pretty simple. So we know A squared, so our Mach number equals velocity over the speed of sound. So write this as A equals V over m, and then A squared equals just, that squared. Okay? So we're going to plug this in. So velocity divided by V squared over m squared dV equals negative dr divided by r. We're almost there. This velocity cancels out, that cancels out, m squared goes to the top. We're left with m squared dV over v equals dr divided by r. So now we're going to go back to our conservation of momentum, or our conservation of mass result, which said dr divided by r plus dv over v plus dA divided by a equals 0. Then we're going to plug this into here. So we have m squared dv over v equals negative dv over v minus dA over a. Then moving this to that other side, so we're left with m squared dv over v plus dv over v equals negative dA over a. Then finally, group like terms, and you're left with we should have a negative. I missed something. Hold on. This is a negative dr. So we're going to move the negative to here. So this should have a negative. So my bad. Hold on. That should be a negative. So we're left with 1 minus m squared dv over v, equals negative dA divided by A. This is our big result that we did all that work for. So what does this relationship show us? Like, what does this mean? And this is very important in converging, diverging nozzles. So let's say, so we're using this equation right here. Okay, so let's say the Mach number is greater, well, first actually we do less than 1, okay? So if we do less than 1, this is going to be positive, and that's going to be a negative. But then we'll just copy over the negative, so negative dV over V equals dA. Okay, so what this is saying, that as our area is increasing, our velocity is going to decrease, dA over A. So this is saying that our area is increasing, our velocity is going to decrease, which is not a good result for a rocket nozzle that is expanding. The area is getting bigger, okay? So as it's coming out here, if this Mach number at the choke point, or the throat, is not equal to 1, once it gets out here, when the nozzle starts expanding, if it's less than 1 at this point, then the velocity will decrease as it expands out, which is not what we want. We want, as it expands, that the velocity is going to increase, right? So then going back to our equation here, if we plug in a number, Mach number that's larger than 1, what does that leave us? That leaves us with negative dV over V equals negative dA over A. Negatives can cancel out and they just become a positive. So this is saying, as the velocity is increasing, or as the area is increasing, the velocity is also going to increase, and it causes it to go supersonic. And now, this might not intuitively make sense, but this is all because of compressible flow. You might think of a nozzle on like a water hose, right? So you nozzle it so the water will come out faster. But that's because the water is very incompressible, right? Just like cold, regular water, not incompressible, but like a hot exhaust gas moving very fast, you need to treat that as compressible flow. And we also need to conserve our mass and momentum, and then there's different pressures. So if it's compressible flow, Mach number greater than 1, as it gets out here, the density is decreasing and the area is increasing. So to also catch up with that, to conserve our mass flow rate, because back here we have very high pressure, low pressure out here, but we also have high temperature, a very high pressure, so density is going to be high. Density out here is going to be greater, and then as the air gets out here, that density is decreasing, area is increasing, so to conserve our mass and momentum, our velocity is going to increase at the same time. So that's why we have this important result here, and that's how we derive it. 3 pages worth of work, but try to do it nice step by step to kind of show you how to get it done.